Information transfer from one register to another is described by a replacement operator. This arrow indicates our replacement operator. This R1 arrow R2. This statement denotes a transfer of contents of register R1 into register R2. This transfer happens in one clock cycle. The content of R1 source does not change. Content of R2 will lost and replaced by the new data transferred from R1. We are assuming that circuits are available from the outputs of the source register to the inputs of the destination register, and that the destination register has a parallel load capability. That is, this is our source and this is our destination. So the hardware corresponding to this will be just like the output lines from this register will be connected with the input lines of this register, and there will be some load enable signal that will load the contents to the R2. Okay. Another concept is conditional transfer. Conditional transfer occurs only under a control condition. In that case, while we are specifying in RTL, we can use a control condition and then the operation. So the representation of a conditional transfer will be like this: P colon R2 comma. This is our operation. Then P colon, this will form our control function. So P is a binary condition. P will be equals to either 0 or 1. That determines when the transfer occurs. The content of R1 is transferred into R2 only if P is equal to 1. Based on this will be act as a condition, and if the value of this condition is equal to 1, then only this transfer will occur. That's about the conditional transfer. For example, x dash t1 a b, that is this is our operation. The content of the B register is copied into or transferred into A register, but we have used a control function here. This control function will control the operation, transfer operation. That is, whenever the these are actually two variables, x dash and t1. This is a Boolean function. xt1 is a control function. So whenever the value of the xt1 is equal to 1, this transfer operation will work. Otherwise, the transfer operation will be executed by the hardware only when the Boolean function xt1 is equal to 1. So this xt1 will become 1 when x is equal to 0 and a timing signal t1 is equal to 1, because here we are x complement. Okay, and the variable x is equal to 0 and timing variable t1 is equal to 1. If the value is not, if the value of the control function is a 0, then this transfer will not takes place. That's about the conditional transfer. And we already explained that we can specify hardware, or we can specify our circuit digital system in terms of our register transfer language easily, and we can translate this specification by using a special compiler into corresponding hardware circuit or resistor transistor circuit corresponding to this specification. That will be done by that special compiler, and that will be given into a fabrication lab, and we can fabricate our IC or circuit. So every statement written in a register transfer language implies a hardware construction. Actually, it is a hardware description language, not just like a programming language. It is a hardware description language. So hardware implementation of the statement, above statement xt1 is equal to ab colon. This will be this control function, and the operation will be separated by a colon. So xt1 a gives b. The hardware implementation will be just like we have register B, register A. The output of the register B are connected with the input of the register A. Register A will have another load capability. Whenever this value 1, then the value output, the content on this bus will be captured into register A. If the value is equal to 0, the value will not be captured into register A. So this load is controlled by our control function. That is our hardware implementation. This is our control function. This is the circuit corresponding to control function. That is x dash t1, that is an AND gate. Then that is given to our load. Then consider another two statements in our register transfer logic or language. T1, this is one statement, T1 colon C gives A, T5 colon C gives B, where T1 and T5 are timing signals. That depends on the clock, that is related with the clock signal. This is one timing signal, this is another timing signal. So whenever the T1 will become 1, then this operation will be performed, and whenever T5 will become 1, this operation will be performed. Here the special case is so destination is same in both cases. Here is also C, here also C. Destination register C receives information from two sources, but not at the same time. Timing variable is different. First line states that the contents of register A are to be transferred into register C when timing variable T1 occurs, and second line states that the content of the register B are to be transferred to register C when timing variable T2 occurs. So this is the hardware implementation or hardware corresponding to these two statements, or the hardware circuit generated corresponding to these two circuits. Assume that our registers are 4-bit, that is why 0 to 3 is given there. Register B, register A, 4-bit bus, and to select one register, we have to use one of the source register. We have to use a multiplexer, and here we are using a quadruple 2 to 1 multiplexer because each bus is 4 bits. That is why quadruple. And the selection from these two inputs will be based on the select line, and another line is enable line. This is an active low signal, that is why a bubble here. Whenever this value will become 0, then only the multiplexer will be enabled and the output will be available. When the it is disabled, then this multiplexer will enter into a high impedance state and this line will become a disconnected one. Okay. So if the select line is equal to 1, then this register B will be selected, and if the select line is equal to 0, register A will be selected. Then how this is implemented, how the control function is implemented here. Here this is also a load signal. Then T1 and T5, these are two timing signals or timing function. They are connected with the timing variables. They are connected to an OR gate. So whenever any of these timing variable or timing signal will become 1, then the load signal will be enabled and a enable line will be activated, because here 1, here this 1 will become 0 here, and this mux will be enabled. Both this register and this will be enabled, and this load will become active. And if T5 is equal to 1, then here a 1 will reach, and corresponding to that what will happen, this register B will be selected and reach into C register. And if at T1 T5 will become 0, so this register A will be selected and the content of register A will reach into register C. Okay. Next we can consider the basic symbols for register transfer logic. Letters followed by numerals denotes a register, example MAR R2. Subscript, that denotes a bit of a register, example MAR 0, MAR 1, that indicates first bit in MAR register, second bit or 0th bit in MAR register, and first bit in MAR register. Parenthesis denotes a part of a register, this sub register. We can represent sub register like this. R2 0 to 7 means bits 0 to 7 from R2. Then R2L, that indicates we can divide our for example 16-bit register into two halves, lower half and upper half. For that we can use R2L or high, L or H. Okay. Then arrow denotes transfer information. We already discussed R2 arrow. R1 means the content of R1 is to be copied into R2. Colon terminates a control function. That is also discussed. And comma separates two micro operation. That is R2 is equal to R1 and R1. That will occur in the same clock cycle. That is the meaning. Comma separated micro operations. This actually indicates swap operation. The content of the R1 will be copied into R2 and R2 will be copied to R1. That will take in the same clock cycle. So that will form a swapping operation. Then square bracket. Specify an address for memory transfer. For example, M2000 means the content of the memory 2000, memory location 2000 will be selected. Okay. Thank you.